the clock rolls over to the next hour, and that's when I come into frame and we get started. We are punctual here. All right. So it's, what time is it? It's physics time. Yay. Right. Okay. So I did not get sucked up by a tornado yesterday. So luckily I am back to talk to y'all. So here we go. We're going to do some more AP Physics C level momentum and collisions. My goal for this session is to really make it like AP Physics C level stuff. So if you're tuning in from AP Physics 1, I'm sorry. I will tell you that the last 5 minutes is going to be of interest to you. So if you're watching live, go do something else. Watch it on the rewatch and just go to 5 minus whatever the amount of time the video is where I talk about squared and ABCD. Same goes for AP Physics 1 teachers. Might be of interest to you, but not really here at the beginning, right? Okay, so my name is John Frensley, teach at Prosper High School, 30 minutes north of Dallas, and this is Physics C Mechanics. Here's a bit of a warm-up for you. I guess if you're from AP Physics 1, if you haven't left already, this warm-up could mean something to you, but it's really going to be this and the last 5 minutes. That's all it's going to matter to you. So we got students A and B. They're identical mass, and they stand on identical mass platforms that are initially at rest, and they can roll without friction. Those of you who are from Physics 1 probably can recognize this is a question out of the Physics 1 workbook, right? But I think it's also good for Physics C. So student A holds a ball. You're going to throw the ball to student B catches the ball. Very simple, straightforward, except I'm going to ask you two things about this whole situation. First, who's moving faster after the catch? Student A moving faster, B, or both the same, right? Maybe a little trickier than you think it is. Think carefully. Explain your reasoning, of course. And then let E1 be the mechanical energy before the throw, E2 after the throw before the catch, E3 after the catch. Rank them and explain your reasoning. All right, so I'm going to give you, let's say, a couple of minutes to try these. Write something out. On your mark, get set, go. Branch of the military has its own theme, you know, like Off the Wild Blue Yonder for the Air Force. Well, someday the Space Force is going to get its own theme, and I want it to be either that song or the theme to Star Trek: The Next Generation. People on the rewatch are going back now just to listen to the theme. Like, would that go with the Space Force? Okay, in a change of pace, we're actually going to go over this question at the outset here. So who moves faster? Well, here's what I'm thinking. I'm thinking that the net momentum of this system is always zero. No one's moving before, and there were never any unbalanced external forces. Yeah, weight, normal, but they cancel, right? The A on the ball on B, those are all internal forces, right? So the net momentum starts zero and is conserved, stays zero. After the catch, the system consisting of student B and the ball has the same momentum to the right that A has to the left, making zero net momentum. So A left momentum, B and ball, same right momentum. But here's the kicker, B and ball have a greater total mass. A has less mass than B and ball. So same momentum, A has less mass, A moves faster. Oh, drat. I did not put a slide for ranking the energies. Shame on me. Did I not put a slide for ranking the energies? Well, I guess I'm going to have to talk to you about it the hard way, okay? So here's the ranking of the energies. So energy number, so first of all, mechanical energy is kinetic plus potential, right? Well, in this situation, the potential energies aren't changing, right? The A and B and the ball all keep the same height. So I don't care about potential energy if it doesn't change. However, kinetic energy is definitely changing. So in my mind, B is really mechanical energy is just kinetic energy. So I'm thinking this, energy 1 is kinetic energy of everybody before the throw. That's 0. Energy 2 is the kinetic energy after the throw, and energy 3 is the kinetic energy after the catch. I know energy 1 is going to be the lowest because it's 0, nobody's moving. But I know that when B catches the ball, that's an inelastic collision. Inelastic collisions always dissipate kinetic energy into heat, sound, dissipated forms of energy. So that must mean that energy 3 is less than energy 2 because the catch dissipates energy. So I'm going to say energy 2 is the most, then energy 3 because you dissipate some energy in the catch, finally energy 1, which is 0. Okay, I didn't make a slide for that. Shame on me. Okay, lesson overview. We're going to look at elastic collisions today, and we're going to actually do some quantitative stuff with them. Elastic collisions are terrible, which is why they don't really appear quantitatively in AP Physics 1, but they might appear in AP Physics C. I want to talk to you about them and how you can do them quickly rather than a bunch of math, right? Then we're going to practice some more of these questions where you have to like write and explain your reasoning because it's not something that we're used to doing in AP Physics C. We're used to just mathing and graphing everything out. And then this is one, we haven't done an experiment-based question together, you and I. Now, maybe Ms. J has with y'all. I haven't been watching her videos because I can't even stand watching myself on YouTube, let alone somebody else. But we're going to do an experiment-based question today related to momentum, just to give you some feel for that too, right? Okay, so let's just talk about an elastic collision. So first things first, students think that elastic means momentum is conserved and inelastic means momentum is not conserved. That is wrong, what I just said. All collisions conserve momentum, elastic, inelastic, an explosion, as long as the system is free of unbalanced external forces, then because an unbalanced external force is what changes momentum, right? So if you have no unbalanced external force, then there's nothing to change the momentum. What if you do have an unbalanced external force? Well, you still get the same momentum as conserved if the before moment and after moment, when you're comparing the momentums, are a very short delta t apart. Why? Because it takes an external force time to change the momentum. So if you do have an external force like friction and your before and after are like a millisecond apart, right before and right after the collision, then the delta t is so small that the friction doesn't have time to change the momentum any. So you get to use conservation of momentum just before and just after a collision if those moments in time before and after are like that, like instantaneously separated by a tiny amount of time, right? However, an elastic collision has an additional burden attached to it, and that is that the kinetic energy before equals the kinetic energy after. That's not true for all collisions, only this special type. All collisions have conserved momentum, only elastic collisions also keep the same kinetic energy. So here's a typical elastic collision problem and why they're so awful. So what they're going to do is they're going to give you the masses of the two objects that are going to elastically collide and the initial velocities of both objects. And then it's going to say, what are the two final velocities, right? Now, if this was a sticky together collision, that would be easy because there's only one unknown, the final velocity of the stuck together junk, right? But if there's an elastic collision, and there's two unknown velocities, well, that means you need two equations, and that's difficult. So what are the two equations? First, conservation momentum, which I write as m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. Note I've color coded the unknowns in red. So those white letters you know, the red ones you don't. You can't solve two unknowns with one equation. So you need another equation, and for an elastic collision, It's conservation of kinetic energy, a thing that's not really a law of physics, except in this special case, an elastic collision. You need the kinetic energy before to equal the kinetic energy after. So you have two equations and two unknowns to solve for. Well, friends, like, can't I just do like elimination like I learned in my math class? No, you can't, because the v is squared in these two equations, which makes this much worse than when you did systems of two equations and two unknowns in your math class. They were all linear. Go back and look. There were no squareds on anything. Here there are. So you have to do like a substitution, and then you have to FOIL it out, and then you have to group together like terms. Then you have to do a quadratic formula. It's a nightmare. It's like the worst thing ever. It's all of algebra 2, at least what we call it here in the state of Texas, which is all dealing with quadratics and stuff. I want to teach you an easier way. I want to teach you a way that's so easy, you might even be able to do it in your head. But this is what I tell my students. If I make the difficulty of the math bar go down, then the conceptual bar goes up to compensate. So while the math is easier, you really have to understand the concepts that are involved in order to take this nifty math shortcut. So this might be a good one to watch on the rewatch or pause and review, because everything I'm about to talk to you about is simple, but it's something you've probably never thought of before, and it's important. Okay, so here's an elastic collision. Look at this. We have a 1 kilogram car going 6 meters per second. It collides elastically with that red 2 kilogram car. After the collision, the 1 goes backwards 2 meters per second. The 2 kilogram goes forwards 4 meters per second. You can see that up here in this animation right here. What's going on down here? Down here, it's the exact same collision. It's the same collision, but in a different frame of reference. It's in the frame of reference as if you were walking along with the center of mass of the two-cart system. So an elastic collision is extremely simple if we watch it while walking along with the center of mass. Look carefully at what happens in the center mass reference frame, which I call the CMRF. In the center mass reference frame, these two objects just switch their velocities. Watch as the blue goes from right 4 to left 4 meters per second, and the red goes from left 2 to right 2 meters per second. So as far as the center mass is concerned, a perfectly elastic collision, the two objects come together and their velocities just get negated. That's all that happens. In case you care, in a perfectly inelastic sticky collision, the center mass sees the two objects come together and just stop. That's what the center mass sees. So the center mass sees simpler collisions than we standing on the Earth see, right? So we're going to exploit this simplicity to find a quick way to solve for the final velocities in an inelastic collision. So here's the process. Are you ready? Here we go. 4 steps. Step 1. We're going to calculate the velocity of the center mass. The animation shows it already, 2 meters per second. But how do you calculate that velocity of the center mass? Well, what you do is you say, okay, momentum equals mv. For a single object, momentum equals m, the v of the object. But for a system, the momentum is the net momentum of the system, the mass is the total mass, and the v is the v of the center mass. Same equation, but for a system now rather than a single object. So that means that the center mass velocity is the net momentum divided by the total mass. So where do I get 2 from? I take the net momentum of the system, which is same before and after. So that's 6 times 1 plus 2 times 0. That's a net momentum of 6. Divide by the total mass of the system, 3 kilograms, and you get 2 meters per second. Step 1, get the speed of the system center mass. Step 2, now we're going to jump out of the Earth reference frame and into the center mass's reference frame. Imagine the center of mass was like a little cart that happened to be traveling past you. You're standing on the Earth and you're watching these two red and blue carts collide. But then where that arrow that says CM is, imagine instead there's a little roller coaster cart that just rolls past you. You're going to jump in that cart and you're going to see the collision from a new frame of reference. So how do you jump into a new frame of reference? You subtract that frame of reference's velocity from everybody. So look carefully. In the Earth frame of reference, it's 6 rightward meters per second. In the center mass reference frame, it's 4 rightward meters per second. You subtract the center mass's velocity from everybody to jump into the center mass reference frame. In the Earth frame of reference, 0 meters per second. In the center mass reference frame, -2 meters per second. We subtract 2, the center mass velocity, from 0. Then we apply the collision. How do we do that? We just switch the signs on the velocities in the center mass reference frame. So in the center mass reference frame, blue goes right 4 meters per second, now left 4 meters per second. In the center mass reference frame, red goes left 2 meters per second, now right 2 meters per second. Now we're going to jump out of the center mass reference frame and back onto the Earth. So if we jump from Earth to center mass reference frame by subtracting VCM, then we're going to add VCM back to both velocities. We're going to add it back to both velocities. So I'm going to talk about this, and I'm going to apply the steps to this animation. In this animation, V1 initial is 6, V2 initial is 0. So how do we get the V of the center of mass? We're going to take the net momentum, mv of the blue plus mv of the red is 6, over total mass is 3, that's 2 meters per second. Then we're going to jump off the Earth and into the center of mass's reference frame by subtracting the V of the center of mass from everybody. The V of the center of mass is +2, so subtract 2 from 6. And the blue in the center mass reference frame goes 4, right. Subtract 2 from 0, and the red goes 2 left, -2 meters per second in the center mass reference frame. You can see that in the animation before the collision. Here's the 4, here's the -2. Now we're going to make the collision happen, which means we just switch these two signs. Now, finally, blue goes 4 left, red goes 2 right, in the center mass reference frame. So to jump back onto the Earth and plant our feet on the ground again, we're going to add the center mass velocity back. The center mass velocity was 2. So we're going to add 2 to both of these. Add 2 to -4, and you get -2. Add 2 to 2, and you get 4. And that's the final velocities here. Watch carefully. Up here in the Earth reference frame, you can see the -2 on the 1 kilogram cart and the +4 on the 2 kilogram cart. Yes, I know it's a 4-step process, and each step seems kind of weird. The one that gives my students the most trouble is just getting the center mass velocity, which is total momentum over total mass, right? But once you do that, take it away from everybody, switch their signs, then add it back, right? All right, so here's some guided practice for you. You're going to try it right now. You're going to get a couple of minutes here, 2 different numbers here. So we have a 4 kilogram object moving to the left with initial speed 6 meters per second, collides elastically with a 2 kilogram object initially at rest. What's the final velocity of each object? I'm treating right as positive, so we're starting with a negative initial velocity. Deal with that. On your mark, get set, take a stab at it. Oops. All right, a little bit less music than we had time, but okay. So let's go through this together. All right, so here's what I'm thinking. I'm thinking I need to get the center mass velocity. So I'm going to take the net momentum, which is going to be 4 times -6, -6 for leftward velocity, and 2 is at rest, so it doesn't contribute any momentum. Net momentum over total mass. Total mass is 6, 2 plus 4 kilograms. Net momentum is -24, so that's -4 meters per second worth of velocity, right? Okay, so now what am I going to do? I'm now going to think in terms of what the center of mass sees. So to jump into someone else's reference frame, you subtract their velocity from everybody. So I'm going to subtract -4, add 4, to each velocity in the Earth reference frame. So taking -6 and subtracting -4, I now get, let's see, this is, uh, did I do this correctly? Okay, I guess I'm treating V2. I think I'm treating V2. V2 is the larger object. Okay, sorry. I'm sitting here, I'm like, wait a minute, that doesn't make sense. So V2 is the larger object. So I'm treating the 4 kilogram as if it has -2 meters per second. So I said, okay, take -6, that's the 4 kilograms speed, velocity, subtract -4 from -6 and you get -2. Now the 2 kilogram, the lighter one, is going 0. So subtract -4 from 0 and you get 4 meters per second. So I'm sorry, I'm following this convention I personally have, which is that 1 is the lighter and 2 is the heavier object. Excuse me. Okay, so what am I going to do now? I'm now going to reverse the velocities. When the collision happens, the center of mass sees 4 right meters per second become 4 left meters per second, 2 right meters per second, left meters per second become 2 right meters per second. So when the collision happens, the velocities switch. So this is now V1 final, V2 final, where V1 is the lighter object, right? Now I'm going to add the center of mass velocity back. I'm going to add the center of mass velocity back to jump back into the Earth frame of reference. So I subtracted the center of mass velocity from everybody, switch their signs, then add the center of mass velocity back. So I'm going to add -4 back, and the lighter object is going to go 8 left meters per second. I'm going to add the -4 back, and the heavier object is going to go 2 left meters per second. So that was the 2 speeds you should have gotten. And now let's see what happens if I animate it. So here's what the animation looks like. All right, there's my 6 left meters per second. And right before the 2 goes out of frame, you can see the 8 meters per second and the 2 meters per second, both to the left. All right, isn't that lovely? Okay, so oops. All right, this is a tricky one. Okay, this has shown up a couple of times on the AP exam, and of course it would have 2 objects that are bouncing together by springs, and it would say, what is the most compressed that the spring ever gets? Well, of course we can't ask you to do math on this AP exam, but we can certainly ask you to explain what you would do to calculate this maximum compression. So suppose you know the mass of both carts, their initial speeds, and the spring constant of the spring. Those are the 5 numbers that you have access to, right? 2 masses, 2 initial velocities. I should say velocity because there might be a sign associated with it. And the 5th thing you know is the spring constant of the spring. Explain how you could use this information to determine the most compressed that the spring ever gets. And this is a lot more tricky than you might think. In fact, if I was writing your C exam this year, I would have put this on it, right? So I give you some hints because it's so tricky. So I want you to think, when the spring is most compressed, what is true about the 2 carts' motions? In fact, I'm going to go back to this animation here. I'm going to give you one chance to look. When the spring is the most compressed, what is true about the 2 motions? Okay, so you saw it. That was your chance to see it. What is true about that moment when the spring is the most compressed? What are you going to say about the momentum of the system? What are you going to say about the energy of the system? And what related to momentum or related to energy are you going to need to calculate? So you're going to talk about what you're going to need to calculate. All right, so I'm going to give you 3 minutes on this difficult one. On your mark, get set, 3 minutes. right, this is the part where you get mad because the answer is probably a lot simpler than you thought it was. So here we go. First of all, look at that animation. What do they have the same at the moment the spring is the most compressed? They go the same velocity. So I'm going to make that assertion first. The spring is the most compressed when they both have the same velocity at that instant. It's not forever, it's an instant. But what I'm going to do is I'm going to treat this as a temporarily inelastic collision. Yeah, the collision is perfectly inelastic right now, only at that moment when the spring is the most compressed. So I'm going to say, hey, solve for the V the two carts have at the moment of maximum compression by treating it as if it's a perfectly inelastic collision and solving for the perfectly inelastic collision velocity. So if you were to give me, okay, let's just talk about the actual information here, okay? So we have 4 by -6, that's the total momentum, equals 6 times what? So the answer would be -4. So the velocity at the moment they have the same speed and the spring is most compressed is when both those numbers are -4 right now, okay? So now what am I going to say? Now let's talk about energy. I'm going to get the initial kinetic energy of both objects, the total initial kinetic energy, 1/2 mv² for both. And I'm going to get the final kinetic energy at the moment that they move the same speed, doing a 1/2 mv² there. So I have a couple of 1/2 mv² before, a 1/2 mv² after. Those amount of energy, those total energies will not be the same. The difference between the initial and final is at the moment when the spring is most compressed. Final is right now, okay? So the difference between initial and final kinetic energy is the energy stored in the spring. So then I'm just going to plug that energy, that's the potential energy, into like 1/2 kx² and solve for x. So once again, I find the speed when the two objects have the same speed as if they were temporarily making an inelastic collision. I get that kinetic energy at that moment, the initial kinetic energy of everybody, and they're different numbers. The difference is the potential energy stored in the spring. Set that potential energy equal 1/2 kx² and solve for x. Yeah, it's harder to do with math, but it's not that difficult to explain now, is it? Okay, here's a bonus question. You're going to get 2 minutes for it. So suppose that you have the cart of mass m is moving with speed v0 toward a cart of mass little m, and we're going to have an elastic collision. It turns out that if the big cart is way, way, way more massive than the little cart, that's what the double greater than sign means, way, way, way more massive, there's a fastest possible speed that the little mass can attain as a result of this collision. So students think that if the big mass doubles, then the velocity of the little cart from the elastic collision will also double. But no, it turns out that you can make the big mass as big as you want, and there's a limit to how fast that little cart will go. So you're going to get 2 minutes. Can you reason it out? On your mark, get set, go. naught. So what I'm going to do is I'm just going to apply the same steps that I just did for y'all. And I'm going to make one little argument in there. You'll see what it is in a moment. So V1 initial, so this is the littler mass. Excuse me, this is going to be the bigger mass now. So V1, 1 is going to be the big mass and 2 is going to be the small mass. So the big mass is going V0, the small mass is not moving at all in the Earth frame of reference. So let's calculate the speed of the center of mass. I'm going to take net momentum, which is big M V0 because it's moving. Little m doesn't contribute any momentum, and divide by big M plus little m. Now I'm going to make an argument here. If big M is way bigger than little m, then the sum of big and little m is basically the same as big M. So if you take big M times V0 and divide by something that's almost the same as big M, then the big M's cancel out and you just get V0. So when you have two objects, one super heavy and one super light, the center mass velocity is the same as the velocity of the heavier object. Okay, let's jump into the center mass reference frame. We're going to subtract V0 from everybody. So we subtract V0 from the big object, and he's not moving because in the center mass reference frame, the big object is the center of mass. And then the little object is actually moving toward. So instead of seeing this, instead of seeing big object moving toward little object, then instead we're going to see the big object standing still and the little object going to boom right off of it. So the little object was moving left. Now it's moving right. So I'm going to apply the collision, and the little object, which was moving left V0, is now moving right V0. Well, if we jump back into the Earth's frame of reference by adding the V0s back, then what actually happens is that the big object does not noticeably slow down, and the little object will have twice the velocity of the big object. So if you have a gigantic object that elastically collides with a little object at rest, the little object cannot obtain any better speed than twice the speed of the big object, right? So there you go. It's a little factoid. I don't know if you'll ever need to know it. Okay, so I wanted to come up with an inelastic collision question. It's like the easiest question in all of physics, where it's like, hey, 2 kilograms moving 6 meters per second collides with 4 kilograms at rest. They stick together. What's the velocity after the collision, right? It's like the easiest thing in the world. It's pathetic. So I'm like, hey, how can I see it up, right? Like make it physics C. So I came up with this. This is the hardest inelastic collision question you're ever going to come up with. Block A is given an initial push, so it slides across a rough table. Oh, there's friction, starting at time t equals 0. Block A collides with block B at time 4 seconds, and they stick together. It should have said they stick together, and they come to rest at time 5. So that's an important piece of information I forgot to write down. They stick together at time equals 4. Here's the position of block A. X equals negative 2t squared plus 26t before 4 seconds. X equals negative 2t squared plus 20t plus 24 after 4 seconds. So I asked this really easy 50-50 question. Which block has greater mass? Remember, they stick together at time equals 4. Can you see through all the hogwash and figure out the simple way to do this? Well, you got a couple of minutes, so good luck. 3 minutes. probably end at 50 after the hour, so I hope you don't mind. Wow, I was just given a piecewise position versus time function. What do I do with that? Well, here's an idea. Momentum depends on velocity. So why don't you take the derivative of everybody? So here's the piecewise position function. Let's take the derivative of all that. So the derivative of the first piece is negative 4t plus 26. The derivative of the second piece is negative 4t plus 20. Now, what am I going to do with that? I know. I want to find out the speed just before and just after the collision. All the frictiony, slidey time I could not even care about. What I do care about is the velocity right before and right after the collision. So let's plug a time of 4 into the before velocity and plug a time of 4 into the after velocity. Plug 4 into the initial velocity and you'll get 10 meters per second just before the collision and 4 meters per second just after the collision. Now, if I walked up to you and said, hey, block A has 10 meters per second, and when it sticks and hits and sticks to block B, they have 4 meters per second. That's a lot easier question. Which one is a greater mass, right? Because all you had to say is well, wait a minute. If the two masses were equal, then the velocity would be cut in half. But if B is heavier, then the velocity would be more than cut in half. It would be cut down to something smaller. Well, that's the case here. In this case, because we go from 10 to 4 meters per second, the total mass went from 1 to 2.5 times as much. So that means that B has more mass than A because the total mass more than doubled, right? Specifically, B has 1.5 times as much mass as A if you want to go that deep into it. So there you go. I gave you this big long function that was a nightmare, and all you had to do is take the derivative and plug in the changeover time into both of them. Yeah, it really wasn't that bad. Okay, this is what we want to end on today. So we're going to end maybe 10 after 50 after the hour. I hope you don't mind. This is a cart that's being filled with water while it's rolling. So let's say you have a toy cart that can roll without friction on a flat track. You allow the toy cart to pass under the spout that's going to empty water into the cart, as you can see in the diagram. And your lab partner watches this and he's like, hey, is momentum conserved? Is kinetic energy conserved? Are they both conserved? Is neither one conserved? You're going to come up with an experiment to test which one or both or neither are conserved. So this is our experiment-based question today, our practice for that. I originally wrote a question like this to review P1 students, but I think it might be a good one for y'all, so I'm giving it to y'all here in Physics C. So it is not possible for both momentum and kinetic energy to be conserved. That is impossible in this situation. So I want you to give me a little ditty as to why. I'm going to give you 2 minutes. Just give me the littlest ditty that you can, why it is that you can't conserve them both. Yes, and if your high school's marching band does the Rusty Bucket Bay theme from Banjo-Kazooie, I will fly out to your state to watch it. Okay, here's the deal. Why can you not have both of them conserved at the same time? So here's what I said. You could probably say it faster. P equals mv. So if momentum's conserved and the m doubles, then the v has to be halved. They have to go up and down by the same factor. Here I said 4 times. So I said if momentum's conserved, 4 times the mass is 1/4 the velocity because they're inversely proportional. If kinetic energy is conserved, 4 times the mass is 1/2 the kinetic energy, 1/2 the velocity, because the v is squared. Well, see, that's a contradiction. You can't have them both at the same time. You can't 4 times the mass and 1/4 the velocity to make momentum happy, and at the same time 4 times the mass and 1/2 the velocity to make kinetic energy happy. You can't make them both happy at the same time. It's one, the other, or neither. So here we go. Here's going to be 5 minutes. You wish to determine which quantity, if either, is the quantity that's conserved in the collision. So you're going to formulate an experimental procedure now to make measurements that would allow you to make this determination and explain how the measurements would be used to draw your conclusion. This is a big one, so you're going to get 5 minutes on this one. On your mark, get set, go. Write an experiment. apologize for going over time. This is the last thing we're doing here. I can hear the scream of 1,000 AP Physics C teachers saying, this is based on that problem from the 90s. This was on the AP exam in the 90s, except in the 90s, it was like all derive equations using symbols, right? I just converted it into a experiment-based question. And in case you care, it is actually momentum that's conserved. Kinetic energy is not conserved because every single droplet that lands in the cart makes basically a perfectly inelastic collision with the cart, and perfectly inelastic collisions dissipate kinetic energy. So here's a rubric for you based on what you wrote, okay? Did you talk about measuring the mass and say what you would use to measure the mass? This is a toy cart, right? So maybe you could measure the mass using an electronic balance, right? Did you talk about measuring the mass before and after the water empties, right? That's important. Did you talk about a way to measure velocity and the equipment you could use? It could be as simple as lay out a meter stick and time how long it takes the cart to pass the meter stick, right? Or you could talk about using motion detectors or photo gates. If you talk about photo gates, make sure you say that the photo gate measures the time that the cart blocks the photo gate, and the length over time is the velocity. You have to say that specifically if you talk about photo gates. Did you talk about the fact that velocity before and after the downpour needed to be measured? Okay, so we got mass velocity before, mass velocity after. So what are we going to do? We're going to do mv before and mv after and just compare the two numbers. We're going to do 1/2 mv squared before and 1/2 mv squared after and compare them. And no, you don't get to use any formatting on this exam, so I would write it as 1/2 mv caret 2 to communicate 1/2 mv squared, right? Okay. Here's, I had a teacher contact me through Facebook the other day, and they said, hey, I've heard of this acronym called SQUARED for how do you make sure that you've written everything in a lab procedure you need to write. So I'm going to just go over that with you all here. This applies to all levels of AP Physics. So when you write a lab procedure, this acronym SQUARED is a checklist. It's not an order, it's a checklist to make sure you've said everything you need to say. So S is talk about the setup. Don't say anything that the picture, which D is going to be diagram, don't say anything that the diagram says, but you need to talk about anything that maybe isn't clear from the diagram, right? Q and U is the quantities you need to measure and the units. Okay, now you don't have to put the units, you don't have to say measure the length in meters. Like, you don't have to say that on the AP exam, but I found that if students say that, it actually helps them. Like, it helps their thought process, right? It annoys the reader because it's extra information, but I don't care about the reader, I care about your thought process, right? A is apparatus. Say what you're using to make measurements. Don't just say measure the mass of the cart before and after. Measure the cart with an electronic balance before and after, right? Measure the distance with a meter stick. R is any repetitions you're going to do. So are you going to make the speed of the cart be different on every trial for some reason? Maybe that's important to the question that's being asked, right? Remember, every experiment is to answer a question. So if it says, is momentum conserved for lots of different speeds? Well, I'm going to repeat for lots of different speeds, right? How are you going to reduce error? Are you going to use a photo gate or something like that, a motion detector, instead of a meter stick and stopwatch in order to reduce error? Talk about how you're going to reduce error. D is the diagrams and the labels. And then I wanted to throw this in there. Your AP exam in Physics C and the ones in P1 and P2 are going to have a lot of parts where you have to explain your reasoning or justify your answer. So I have a 4-step checklist for that too. Again, it's not necessarily an order, it's a checklist. Did you do these 4 things? A, B, C, D. A, did you clearly answer or answer the question? Okay. Is block A bigger or block B bigger? Say clearly which one it is, right? B is statement, 1 or more statements of basic physics. Could be a basic equation if that might help you out. It's going to be relevant to the situation, but it will never be a false statement. And then C, you're going to connect to what's going on here. Talk about what's going on in this situation. Talk about the physics quantities like momentum, acceleration, whatever. And then D, draw your points together and connect them to your answer. So I did that here with an example. So I'm not going to read the example. It's just a block hanging from a string. And in case A, the dart bounces off the block, and in case B, the dart sticks to the block. You've probably seen this question before, P1 and C mechanics. So which one makes the block swing higher? Is it the dart bouncing off that makes the block swing higher, or the dart sticking that makes the block swing higher? So here's my answer choice and my answer, and I've color coded. B is all the basic physics, which is in blue. The momentum is conserved in a collision. Momentum is negative if an object moves backwards. Those are always true. When an object swings upward, kinetic energy becomes potential energy. But C in yellow is where I'm connecting to this situation. In both cases, in this situation, the momentum is the same before and after. The the dart has negative momentum in case A. I'm talking about this situation right there. And then I actually put my assertion at the end. I just say, if you're going to answer the question, answer at the very beginning or the very end. Don't put the answer somewhere in the middle. And then you see the green part where I'm kind of connecting my points together. So I'm not going to read my answer to you. You can push pause if you want and see how each one is each letter. But I will tell you that I pushed this really hard in my P1 and P2 classes, and my C students are going to have to review this year because they took P1 with me, because they're going to be doing a lot of explain your reasoning, and so will you on this year's exam. All right, please don't forget that I have a Friendly Physics Facebook page where I post questions daily with solutions the next day that are aligned with this year's exams. And I'll see you tomorrow. Have a good one.